everyone, thank you so much for clicking onto the video. Here are today's learning objectives. So the first is to look at calculations to determine the percentage yield of a reaction or related quantities and also the atom economy of a reaction. We're then going to look at the techniques and procedures required during experiments requiring the measurement of mass, volumes of solutions and gas volumes, and also the benefits for sustainability of developing chemical processes with a high atom economy. Now we're going to have a look at percentage yield. So what the percentage yield tells us is basically the practical efficiency of a process. So how much is lost by the practical process of obtaining a product, and also by the reactions that don't go to completion. So sometimes we get reversible reactions, or sometimes they're kind of in equilibrium. So we don't get the reaction which fully goes to form all the products. And so the percentage yield can be calculated by doing the mass of product obtained over the theoretical mass of the product multiplied by 100. And we can also do this by dividing the moles of the product obtained and the theoretical moles of product, also multiplied by 100. So in this example, if we started with 3.32 grams of potassium iodide and added 6.62 grams of lead nitrate, find the percentage yield of lead iodide produced. So the first thing to do with all of these kinds of questions is firstly to write out the equation so we know we can see what's happening. So we have potassium iodide, and we're adding this. This should be aqueous, so dissolved in water or solution, and we're adding it with lead nitrate, and this will also be aqueous, and this will go to form our lead iodide, which will now be a solid. And then we also get potassium nitrate, and this will be aqueous. And now we need to balance this equation. And so we see that we need 2 iodines because we have 2 on the right hand side. So that means we need 2 of these potassium iodides. And that means we'll need 2 of these potassium nitrates because we have 2 potassiums on the left hand side. And so now all of these should add up. And so the next thing we do is we work out the moles of potassium iodide and the moles of lead nitrate that we have. So firstly, the moles of potassium iodide. So we know that moles is mass divided by the MR. So we have that the mass of potassium iodide is 3.32 grams. And then we divide it by the moles, which can be found by adding up all of the individual relative atomic masses of the elements. So we have 1 potassium, so we have 39.1, and then added with an iodine, which has an AR of 126.9. And so this gives us 0.02 moles. And then we work out the moles of lead nitrate that we have. So we have that the moles of lead nitrate is equal to, again, the mass over the moles. So we have that the mass is 6.62. And then we divide it by the sum of all the ARs. So we have lead, which is 207.2. And then we have 2 nitrogens, so that's 28.0 because 1 nitrogen is 14. And then we have 6 oxygens, and so that would be 96.0. And so this gives us also 0.02 moles. And now we need to look back at the equation to find out the ratio. So we know from the equation, so we have from equation, two moles of potassium iodide, so we know the number of moles because of this coefficient here, react with 1 mole of this lead nitrate. And so first looking at our first scenario that we could have, if we have 0.02 moles of potassium iodide, so we have 0.02 moles of potassium iodide, then this would react with 0.01 moles of lead nitrate because it would react with half the number of moles of this potassium iodide because it's a 2-to-1 ratio. And so we have moles of lead nitrate. And if we looked at a different scenario that we could have is that if we had 0.02 moles of lead nitrate, so starting off with the right-hand side this time, then this would react with 0.04 moles of potassium iodide, because this time it's a 1-to-2 ratio. So we have we need double the amount of moles of the lead nitrate of potassium iodide. And so we can see that this one at the bottom can't happen because we don't have enough of this potassium iodide. And so this is the reaction which happens. So we can also say that the lead nitrate will be in excess because we actually have 0.02 moles of this lead nitrate, and we're only reacting 0.01, so we'll have some left after the reaction. And so we say that lead nitrate is in excess. So that is the reagent which is in excess. And so now we can work out the maximum mass, so the theoretical mass of this lead iodide that we could form. Because again, we can use the ratios. So going back to the equation, we have that 2 moles of this potassium iodide will form 1 mole of this potassium iodide because there's a 1 here. And so it's a 2-to-1 ratio. And so we're reacting 0.02 moles of potassium iodide. And this will form 0.01 moles of this lead iodide because it's a 2-to-1 ratio. And so now we can use this to work out our theoretical mass. So we have that the mass of Ki, which is theoretical, so the maximum it could be if we have nothing lost, would be moles multiplied by the MR, because we need to rearrange the equation we have for moles. So we have that the moles is equal to mass over MR. So if we rearranged it to get mass as a subject, we would have mass is equal to moles multiplied by the MR. And so this is what we're using. And so we have that the moles is 0.01. So this is supposed to be potassium iodide. So it's the theoretical mass of potassium iodide that we could obtain from this experiment. And then we multiply it by the MR, 207.2 plus 2 iodines, which is 2 multiplied by 126.9. And so this gives us 4.61 grams. And this is what we call our theoretical mass. So now we can work out our percentage mass. And we do this by using the equation we learned before. So we have the percentage yield, is equal to our obtained mass of lead iodide over our theoretical. So of course this would be the percentage yield of this lead iodide. And so if I told you that the obtained mass of lead iodide was 4 grams, then we would have 4 divided by 4.61 multiplied by 100, because this is what turns it into a percentage. And this gives us 87%. So the yield is actually quite high. Now we're going to go on to atom economy. So the atom economy tells us, in theory, how many atoms must be wasted in a reaction. So the way we work this out is dividing the mass of the desired product by the total mass of the reactants. And so, for example, we're going to look back to our example when we worked out the percentage yield of the reaction between potassium iodide and lead nitrate. So our equation was that 2 moles of potassium iodide reacted with 1 mole of this lead nitrate to form 1 mole of lead iodide and 2 moles of lead nitrate, potassium nitrate. And so the first thing we do is work out all of the masses of the desired product and the reactants. So we have that PbI2, which is the lead iodide. The mass of this is equal to its MR. So we have lead, which has an AR of 207.2, and then we add 2 times the iodine, which is 126.9. So this gives us 461 grams of this lead iodide. And then we have the reactants. So we have 2 moles of this potassium iodide. And so we have to do 2 multiplied by the MR of potassium iodide. So we have 2 times 39.1 plus iodine, which is 126.9. And this gives us 332 grams. And then we have lead nitrate, which is equal to 207.2 plus 2 times nitrogen, which is 2 times 14, plus 6 times the AR of oxygen, which is 16. And this gives us 331.2 grams. And so it's really, really important to remember that we don't work out the mass of the product, which is just the byproduct, because we're looking at atom economy. So actually how many atoms are lost when we want to get to our product, so the one that we actually want. So now we use the equation, and we have the percentage atom economy is equal to the mass of our desired product, which is the lead iodide. So we have 461 divided by the mass of the reactants, so 331.2 added with 332, and then multiplied by 100, and this gives us 70%. So it's actually got quite a high atom economy as well. So now we're going to have a look at some advantages of having a high atom economy. So firstly, we're going to look at some economic advantages. A company using a process that has a high atom economy will make more efficient use of its raw materials. And so less money is wasted if more of the reactants actually produce the desired product instead of producing lots of byproducts. And the company will also have less waste to deal with, and so they can spend less on separating the desired product from the waste products. And another thing to note is that any waste products that are produced need to be disposed of safely, and this can also increase costs further. And if chemical companies can find easier and cheaper ways to mass produce medicines and other useful chemicals, then this means that the chemicals can be sold for lower prices and therefore made more available to a lot more people. And now looking at some environmental advantages, we have that waste chemicals are often harmful to the environment. And because if we have a high atom economy, then we produce less waste. And so we'll be doing less harm to the environment. And it can also be difficult to dispose of waste products in a way that minimizes their harmful effects. Many raw materials are limited, and so it makes sense to use them efficiently so they last as long as possible. And high atom economy processes tend to be more sustainable than low, because we use these raw materials for a lot longer before they run out.